So here's a heating curve that shows the whole transition business for water. So we've got temperature on the y-axis, amount of heat added on the x-axis. So you start with some ice, and I believe this is for 1 mole, or 18 grams of ice. You start here at negative 25 degrees Celsius, and you add heat. So as you heat the ice, it's going to warm up. And we've done that before. We've talked about that before. That was that Q equals mc delta T equation. So you can look up the specific heat capacity for ice, and you can find the temperature change. So you can calculate how much energy it would take to go from minus 25 degrees Celsius up to 0 degrees Celsius for a given mass of water. And so you can calculate Q for this step right here. Once it gets to 0 degrees Celsius, the melting point, now you have melting or fusion going on. And so there you're going to use the heat of fusion as a conversion factor. We did an example of that with heat of vaporization. So the heat of fusion for water, if I remember correctly, is 6.02 kilojoules per mole. So if you know how many moles of water you have, you just apply this as a conversion factor. You can calculate the amount of heat needed to melt the ice. Once it all melts, then the temperature can begin increasing again, and the water will heat up as you increase the temperature, as you add heat to it, until it gets to the boiling point. You can calculate the amount of heat here, again using Q equals mc delta T. But now you're going to use a specific heat capacity of liquid water. And the mass of it and this overall temperature change would be from 0 to 100 degrees. Then as the water boils and changes from a liquid to a gas, we're using the heat of vaporization. Heat of vaporization for water is much higher. It's 40.7. I don't expect you to remember those numbers. 40.7 kilojoules per mole. That's why this line is much longer than this line, because you have to add a lot more heat to boil all that water. So the temperature won't change until you've boiled all the water. Then you have steam. And so to figure out how much energy is needed to raise the temperature of the steam from 100 to 125 degrees, you're going to use Q equals mc delta T again, using the specific heat capacity for steam, which is slightly different than that for liquid water or ice. So this is an overall big picture of what happens when you heat a substance. And we can calculate the amount of energy needed to go from any state at any temperature to any other state at any other temperature. When you do a problem like this, you really, really should just make a very rough sketch of the heating curve, because you're going to need a different calculation for each line segment. And then you add the line segments together. I think we've got an example coming up here. Yeah. Calculate the amount of heat needed to take 1 mole of ice at minus 25 degrees Celsius to steam at 125 degrees Celsius. So this is the whole transition. So I'm going to draw just an ugly little heating curve down here. So I'm starting with the solid, and the solid's going to warm up. That's going to be an angled straight line until it starts to melt. I'll have a flat place. Then it'll angle up again until it boils. I'll have a flat place, and then it'll angle up as the steam heats up. So down here I've got a solid. Here's the solid melting. Here I have a liquid. Here I have the liquid boiling. And here I have the gas. I need an equation for each of those, a calculation for each piece. We also need to know the temperatures at which these transitions happen. So for water, it boils at 0 degrees Celsius. Sorry, it melts at 0 degrees Celsius. It boils at 100. We need to know the boiling point and the melting point because when we calculate for these portions, we need the delta T. Q equals MC delta T. So for this portion, the change in temperature is the final temperature minus the initial temperature, 100 minus 0. So for this part, delta T equals 100. What's the starting temperature on our graph here from the question? Negative 25. So we're starting at minus 25, and what's our final temperature? 125. So delta T for this segment, final minus initial. The final temperature for that segment is 125. The initial is 100, so that's a temperature change of 25 degrees Celsius. This first segment here, what's delta T? 25. Final minus initial. The final temperature for that segment is 0 minus the initial temperature of negative 25. That's 25 degrees. Any questions? So here we have the specific heat capacities that we need and the heat of vaporization and the heat of fusion. You don't need to memorize these. They'll be provided either in a table that you can look it up, or they may be given to you with the question on the exam. So we have 1 mole of ice. So this first transition is Q equals MC delta T. We figured out what delta T was. What's the mass of this ice? Well, 1 mole of water, right? And we can calculate the molar mass of water. So it's 18.016 grams of water.
But doesn't the weight change from ice to liquid? Isn't it?
That's a good question. Doesn't the weight change from ice to liquid? The volume changes, the mass doesn't. Yeah. Water is more dense than the ice, but the mass is the same, because mass is amount of stuff, and that doesn't change. So for melting the ice, we have M, 18.016 grams. And then we need to use the correct heat of specific heat capacity. We want the one for ice. So that's 2.09 joules per gram degrees Celsius. And then we're going to multiply by the change in temperature for that portion. We're not going the whole minus 25 to plus 125 in one thing. Each of the segments has its own little calculation. So we can calculate what that is. I'm going to do that later. Here, where we're melting the ice. So we've got 1 mole. Let's start here. 1 mole of water, or ice, and we're just going to multiply by the heat of fusion. 6.02 kilojoules for every mole of ice that we're melting. So since this is 1 mole, that ends up being pretty simple. Heating the water, Q equals MC delta T again. So our mass is the same, but we're going to use a specific heat capacity now for liquid water, which is 4.18 joules per gram degrees Celsius. And we're going to use the change in temperature for this part, which is 100 degrees Celsius. When we boil the water, we've got 1 mole times the heat of vaporization, 40.7 kilojoules per mole. So that's going to be 40.7 kilojoules of energy. I'm gonna erase this here. The temperature change here was 25 degrees, so, but I need that space. So heating the steam, we got the mass again, 18.016 grams. And now we're going to use the specific heat capacity of steam, 2.01 joules per gram degrees Celsius, times the change in temperature there, which we determined was 25 degrees Celsius. So, doing some math here, I'm going to calculate the energy needed to heat up the ice at 941.336. And the unit there is joules. And then to heat the water, that one is 7530.688 joules. And then heating the steam, (905.304 joules. So we've got this amount of heat needed to heat up the ice until it gets to the melting point. This is the amount needed to melt the ice. This is the amount of energy needed to heat the water to the boiling point. This is the amount of energy needed to boil the water. And here is to heat the steam. We need to add all 5 of those together. 3 of them have units of joules. 2 of them have units of kilojoules. Right? Yeah, it is funny. I'm going to convert the joules to kilojoules. So I'm going to have 0.941336 plus 6.02 kilojoules plus 7.530688 plus 40.7 plus 0.905304 equals. So I add all of those up and I end up with 56.097328 kilojoules of energy. In terms of significant figures, adding in kilojoules, this is the one with the fewest number of decimal places. So it's going to be 56.1 kilojoules.
So the kilojoules are the flat part.
Yeah, this one here is melting of ice, and this one's boiling. Yeah, so this is fusion, and this is vaporization. And those require more energy in general than the heating of any of the portions. Any questions? So I can almost guarantee you there will be a problem on an exam that needs you to do this. But it probably won't be cold ice to hot steam. It might be ice at the melting point to water at 95 degrees. It can be any portion in here. We can pick any point along this line and go to any other point and calculate it. You can also calculate the amount of energy released going backwards. And that can kind of mess with your mind. What I would encourage you to do, if they talk about freezing something and how much energy is released, or cooling steam or anything like that, I think it's more straightforward to think of it in terms of adding heat. Do the whole calculation and say, okay, that's the amount of heat to go in the forward direction. It's asking me how much would be released. I'm just going to change the sign. It's going to be negative. So none of the individual calculations in here are very complicated. We've done Q equals mc delta T before. This one with the heats of vaporization or fusion is actually even simpler. It's just dimensional analysis, really. The thing is figuring out where to start, where to end, how to put all the little pieces together. It requires a bit of practice, and you really have to write stuff down and show your work.